Great. So it's nice to meet everybody in a virtual conference. I'm the CEO and co-founder of Cleanlab. This is a company that came out of MIT, co-founded by three of us, three PhD students from MIT. Two of us have graduated, one's finishing up. Anish Athalye is our CTO. If anybody has heard of the missing semester of CS courses, he created those and a bunch of projects on GitHub. If you've ever like managed your dot files or done a bunch of parallel distributed operating systems work. And then our chief scientist is Jonas Mueller, who built AutoGluon. If folks are familiar with AWS or AWS SageMaker, that runs on the AutoML that runs on is something that Jonas was building for 4 years before joining us. And these are really good friends, and this is stuff that we've been working on and talking about for almost a decade. And so I'm really excited to share with you guys. Awesome. Yeah, try to avoid segmentation issues. Hopefully we can address some of those with Cleanlab too. All right, so let's just jump in. The talk should be pretty fun. So first I'll chat a bit about millions of label errors and the 10 most common machine learning benchmark data sets. And that should be a surprise if folks haven't seen the work. We've been benchmarking the field of machine learning on test sets. And it turns out that those test sets, the ones that the entire field is benchmarked on, actually have millions of errors in them, which is shocking. And it means that some of the rankings of benchmark models are actually off. And we'll go more into that. We had some work in NeurIPS, which you can check out. This is built on a theory that we developed at MIT called confident learning, which is a subfield of machine learning for learning with noisy labels, finding errors in data, estimating uncertainty in data. And we'll chat a bit about that. And then we'll chat about why this is important. Why do we want to have AI for data correction? I think everyone has seen by now in the talks that data-centric AI is useful. You're in a Future of Data-Centric AI conference. You're probably on board. But we'll focus specifically on data correction. And then I'll chat a bit about what we're open sourcing and what we're giving away and hoping that people will use more and more. We have an open source package called Cleanlab that's growing pretty quickly. And our goal is to make this a foundational general standard tool for data-centric AI everything. And so we're just adding a lot to it. You can check it out. And finally, I'll share something called Cleanlab Studio, which allows you to do all this stuff with no code automatically. So let's just jump right in. So this is an image I took when I was working at FAIR in New York in Jan LeCun's group. And Jeff Hinton was visiting. And I'm sharing this because a lot of people know these two folks in the screenshot. But what was interesting was Jeff Hinton was giving a talk on capsule networks. And at the end of the talk, he wanted to share his big result, which was that he found a label error in MNIST. And at this time, that was a big deal. Most people weren't focusing on this. This is from like 2016. And so his culminating result, and he's like one of the biggest minds in the field, the culminating result was that there is one label error in MNIST. And I share this because it shows where things were in 2016. Like it was exciting to find one label error. And today we're finding millions and we're doing it automatically at scale. And so the sort of big idea here is that it shows where the progress is over time and that some of the biggest minds in our field are focused on this problem. And this is an example of an MNIST image that was actually labeled 3 in Jan LeCun's data set. And they're old friends, so he's like giving them a hard time. So I was thinking, at the time, back in 2016, I'm like, the MNIST data set at that time had been cited like 30,000 times. And so I was like, hang on a minute, if the field has been citing this 30,000 times as being error-free, what if it actually has errors? Like, what is the implication for the field of machine learning as a whole? And what can we do about that? And so there was some work that we published along the way that I definitely recommend checking out. In the beginning, we looked at the binary classification problem of just how do you find label errors in data and how do you train machine learning algorithms generally for any data set and for any model for binary classification. And then we generalize that for the entire field of supervised learning. And then we, open source this. And so I asked the question, as we were building up this work along the way, what if we just took MNIST and we just ran it through the Cleanlab open source? Like, what would we get? And so I'll show you. Everyone can check this out. Feel free. It's at labelerrors.com. And so this is just a live link. Anyone can check it out. There's ImageNet. We have all 10 of sort of the most commonly cited benchmark data sets. And you can see that, for example, this thing is a baboon, but it's called Siming. This is a red panda, or this is a meerkat, but like it's labeled red panda. We can look at ones that are really easy to see. ImageNet is well known to be a tricky and messed up data set, but like, let's look at Google Quick Draw. So these are a bunch of drawings, and this is labeled t-shirt. It's clearly an apple. This is labeled scorpion. It's clearly a sun. And there are millions of these. Like, you can just scroll through them. This, car was labeled popsicle. It's pretty fun. And there are also, you can check out like any type of data set. So Cleanlab is a general tool for any modality. So for example, these are text data sets where, it says they're very talented, but unfortunately, like, it's an irrational plot and it's a bad movie. And so the label that was given was positive, and you can see, like, we correct that to negative. So you can check this out. There's also an audio data set, but audio is not as good for sharing in presentation, so feel free to check it out on your own. So going back to the slides, and so these were some of the original errors that we found in MNIST, like in the early days. And you can see, for example, this 9 was labeled 8, and this weird 6 looking thing is labeled 0. And so they're like, borderline out of distribution, but they're definitely, errors that shouldn't be in the data set if we're going to say, like, this is a 0. That is a statement, by the way, that gets confusing. Whenever you're thinking about label errors, the question is, like, does an example even have a true label? And often that's actually not true. Like, most examples are somewhat ambiguous. But when we train machine learning algorithms, especially in supervised learning with a single class, we do make the assumption that it has a single label. And so the idea is, can we actually provide good training data? And most importantly, can we provide good benchmarking data? And the folks who are doing the annotations for that data, can we identify sort of what's the most high quality annotations, low quality annotations, and annotators? And so this is a general framework to achieve that. So some quick summary of the results and like why it's important for the field. We looked at 6 image data sets, 3 text data sets, and 1 audio data set. And it turned out that across these, there were millions of errors. Some of them had more or less errors, and I'll show a table on that in a second. But first, I want to say, like, how do we actually find this? And just a real quick question for folks who are listening. If you could post in the chat if you're interested in theory, I'll share a brief sort of theoretical motivation for why this works, especially for data-centric AI in general and these approaches. So I'll keep an eye on the chat. I see a couple folks have said they're interested. So I have various things we can talk about. So I'll include that if there's a lot of interest. So the idea behind finding label errors is that we first have a automated step, and then there's a way to do human verification. So for the research side of things, we use Mechanical Turk to verify, and then nowadays we use Cleanlab Studio. So let me just explain very briefly, how does confident learning work? How do we find these errors? All right, I'll definitely share some theory. Thanks, guys. Good to see you, Elias. In confident learning, the idea is that this is theoretically grounded. So what we can do is we can actually prove, this is pretty cool, we can prove realistic, sufficient conditions where there's actually error in every single predicted probability in a model's output for exactly finding label errors. And that's pretty cool. And we can do that for any data set, for any model. And what it requires is that the model's predicted probabilities are within some range of perfect, but they can all have error. And I'll go into that briefly in a bit. So the neat thing about this is it provides practical algorithms. So they can work on large data sets, unbalanced data sets, for any model and any data set. And so I'll show you just generally how it works. So the idea is that there's systematic errors. So it's actually pretty easy to find random errors. And you'll notice a lot of works will focus on random label flipping. The reason why that's, say you have ImageNet, right? There's 1,000 classes. So if you have 1,000 classes and you have, say, 1,000 errors in ImageNet, that would mean there's only 1 error in every class if you had, uniformly random label noise. So that's pretty easy, right? If you have, say, 100 examples in each class, or in the test set, there's 50 examples. So say you have 50 examples, that means you have 1 error and 49 perfectly labeled examples. So that's actually very easy to find error in random, perfectly uniform random noise. What's more realistic and more problematic is, and real world, is systematic error. So for example, a fox is much more likely to be labeled dog than it is cow. Or like a keyboard is likely to be mislabeled as like a computer than it is, like a banana. And so what you see in real world data sets is most of the error is actually just in a few classes. And can you still find all the errors, even in that case, when you're confusing the model a lot more versus uniformly random? The answer is yes, and we'll show how to do that. So the key idea is, and there's only 3 equations in this talk. This is the first one. The key idea is that you make an assumption. This is an assumption, by the way. that the data itself has no implication on the flipping rate, which is not true, but it is reasonable. So for example, you might have, this might be a person, and if you know that that person is, say, a doctor, then you have some probability that they're interested in medicine. And so different people are interested in medicine. Knowing more information about the person is helpful, but there is, if you do know, this sort of true label Y star, then it gives you a lot of information about your noisy label. Another way to think about this is just like, say you have ImageNet, you have dogs and cats. What this is saying is we don't care what the exact image is of a dog. There's just generally a flipping rate, probability that a dog image is mislabeled as a cat image. And while there are definitely dogs that look more like cats than other dogs, what the notion that this captures is that there's definitely a clearer difference between the probability of like a keyboard being flipped to, a typewriter, than there is like a keyboard being flipped to like a banana, or the wind, or a tree. These are definitely like very different numbers, and so we'll estimate all of these. This will give you a, if you have k classes, this would give you a k by k matrix, and that's what you want to estimate. So that's the thing on the right, and this is the full joint distribution of label noise. And this is what we estimate. This is how we find errors. If you have this thing, you've pretty much solved your problem. So let me just be clear, like this 0.08 down here is saying that if you have say you have 100 examples in your data set, this would mean that 8 of your cow labeled images actually should have been labeled dog. And it would say, for example, here that, you have 20 cow labeled images that are correctly labeled cow. So this fully specifies, or you can say fully characterizes, label noise in a data set. And so that's what we want to estimate. And so we use this method. These are the results on those 10 data sets, by the way. And you can see like percentage error is much higher in like Quick Draw, for example, than MNIST, which had very few errors, but the errors that were in there were pervasive, like, surprising. And some of these have more or less error, and the amount of error definitely impacts the benchmarks. And so I'll show you briefly how. So we asked this question, we're like, okay, there's a lot of label errors in test sets, but like, what is the implication for us as a field and as a society, as a bunch of practitioners who are trying to benchmark and understand machine learning models? Like, the new model comes out, we're going to benchmark it on these data sets, but can we actually trust that it's better than the other ones, given that there's all this noise? And so we looked into that, and this is a paper that was nominated for best paper at NeurIPS last year in the datasets and benchmarks track. And I encourage folks to check it out if you're interested. This is where we looked at all the label errors in the top 10 most commonly cited datasets. And here's the key idea. On the left, you have some trained model that has 100% test accuracy, but your test set has noisy labels. So these things that are circled red is the true label, but you don't know that. You don't get that, right? You have a test set that has errors in it. Instead, this thing looks like green. This thing looks like blue because that's what it's labeled. So as far as you know, your test accuracy is 100%. Now, in the real world, actually, the true label of that, example is red. So the real world test accuracy is 67%. Now imagine that this is a self-driving car. The difference now is the car drives off the cliff 0% of the time, or it drives off the cliff 33% of the time. So you can see how this can be a pretty serious issue if we don't have the real world test performance calibrated to what we observe when we're doing our research papers, or doing our benchmarks. And that's the thing that we want to solve. So this key takeaway is that you need a corrected test set, or you're going to have a this difference between real world performance and what you're measuring. And so what we wanted to know is, like, are practitioners unknowingly benchmarking ML using erroneous test sets? And the answer is yes. And it turned out, which was a very surprising result, that you can see more in the paper, but with just a 6% increase in noise prevalence, it turned out that data sets, for example, in ImageNet and CFAR, you would have something like ResNet 50 actually underperforming ResNet 18. But in the benchmarks, it will look like ResNet 50 is outperforming ResNet 18, but actually what's happening is it's overfitting to the noise. So I don't know if that makes sense, so I'll just repeat it very quickly. If you have just 6% more noise in ImageNet, CFAR, any of these data sets, and then in QuickDraw, the benchmarks are already broken. But in some of the more stable ones that have a little bit less error, if you just bump up the error by 6%, then what you'll observe is that ResNet 18, if you corrected the test set, ResNet 18 actually is outperforming ResNet 50, but you'll never know that. As far as you'll know, using the noisy test data, ResNet 50 will continue to outperform ResNet 18. And that's just because your model has fit to the noise. There's noise in the test set, so it does well on the test set. And then the second thing was that we were really surprised that these test sets are actually a lot more noisy than folks thought. At this point, I want to jump into a bit more about the theory and sort of how do you find this thing. So that was the confident learning. I'm going to jump into my PhD defense slides because there's just a really nice example here that we can just jump into. So let's just look at the top. Typically, I would do this in presentation. As you can see, there's some connecting thing happening. So let's just look at the top. So the idea here is that it's actually really easy to prove that the confident learning approach, which is here, let me just make sure. Okay, let me quickly show the confident learning approach. So if you have, let's go back to our example, right? So a fox is more likely to be labeled dog than, say, bathtub. So this was our joint distribution. And the question is, how do we estimate this thing, right? So this idea is like 3% of your cow images are actually labeled fox. And so we'll look at how do we estimate this. So we only need two things to estimate it. One is the predicted probabilities, and two is the noisy labels. And so, this is just your output of your softmax of some model, and it doesn't matter what the model is or the data set. And these are just the labels that you have. And then what we do is we compute these thresholds. And this is a really simple thing. This is actually just a mean. This is a second equation. And you just take the predicted probabilities for everything that is in class J. So it's labeled J. So these are like, imagine they're labeled dogs, and these are dogs. And you get what's the probability of being dog. And you just take the average. That's it. So this threshold is the threshold for a class dog. The reason why this is useful is because models are not consistent. They're heteroscedastic, meaning that they have different performance for different classes. And most label fixing approaches don't consider this. But actually, it's very problematic because you might have some model that's 10% accurate on some class and 90% on another. So it just tends to have very high probabilities for the class that it's more accurate on. So you want to keep track of a notion of how confident the model is in each class. And then this is a sort of a simplified version of the equation for how we can build that joint. So all we're going to do is look at, for some example, what is the probability that it's class J? That could be like dog. And is that greater than the threshold for the class dog? And if it's greater than that threshold, but it's actually labeled class I, then we're going to count it as noisily labeled class I and actually labeled class J. So that's really simple, right? Like literally, if the probability is greater than some threshold, and we actually prove that that's the correct threshold in the confident learning paper, then you can count up the things that are probably labeled, a dog, but they're actually given the label cat, for example. And you do that for the entire matrix, and then you can, that's how you get the joint. So at this point, I'll just show really briefly. So this is the sort of theory side of things and why you can have a little faith that this is doing correctly. Like that's what we should be asking, right? Like you show a formulation, it looks pretty simple. It seems like it should work. Like let's get some intuition into why it should. So here's the sort of formulation at the top. And I'll go through this really slowly because it's actually really simple and it's really clean. So you'll have to take this for granted, but it's pretty easy to prove. If you have perfect probabilities, meaning you have a model that has no error, then you're going to get you'll exactly find label errors. So just take that for granted. And what we're going to see is if you add error to every predicted probability for each class. So for every class, you add some error term. So the model's like overconfident in some class or underconfident in another. What happens? Is it robust to that? So if you have like a model that's overconfident in certain classes, will confident learning still exactly find label errors? And that's what we're going to check right now. So remember, this is the threshold formulation, and we're going to add an error term, this plus EJ. So for every class, we're going to add error. That could be a plus or minus, right? The error can be negative or positive. So it can be overconfident or underconfident for that class. And we're going to recompute our thresholds. So when you compute a sum with something added, that addition drops out inside of the average, right? So this is going to average out, and you're going to have your threshold that just plus the error. That's your new threshold term for this erroneous predicted probabilities. And now if we look at the Cleanlab formulation, right, we have the predicted probability, which has an error term, and we check, is it greater than the threshold, which also has the error term, and you see that the error term drops out. And so you actually get your original formulation. This here is exactly identical to this here. It's just the predicted probability greater than the threshold. And we've already proven that this exactly finds label errors for this predicted probability, the correct predicted probability. So we've shown that the error term drops out and you still exactly find label errors, even with error in each class. So that's a very simple way to show why there's some intuition here in terms of why you should trust this. And then in the paper, we go more general and we'll show how this works for error in any predicted probability. So hopefully that gives some motivation why you can trust something, a formulation like this, versus just, like, hey, check out some math and trust that it's intuitive. So I wanted to show the sort of obligatory table of, if you look at some of these confident learning methods with recent work in learning with noisy labels, but there's really two things I want to emphasize here beyond just, outperforming, which is kind of like obligatory. There's really two neat things for the data-centric AI community specifically. So the first one is that there's on the right here, what I'm showing is the fraction of the off diagonals in that confident joint. So remember this guy? So the fraction of these that are actually zero, which means we call this sparsity, and it means that the noise is just in a few classes, and that's realistic because in the real world, like, it's very unusual for bathtub to be mislabeled keyboard or banana, right? So there's most of the error rates are actually zero, and that's what this is saying, is that 60% of the error rates are zero. And what you'll see is that the confident learning approaches give you the same performance regardless of how many fraction of zeros there are in the off diagonal, meaning how realistic the noise is. But if you look at some of the previous approaches, you'll see that there's a massive drop off in performance when you make the noise more realistic and less sort of academic in nature. So that's one point. The second point, and this is for the folks who are really, pro data-centric AI, if you look at the ranking and the way things fall out, all the models on the bottom are actually model-centric. So the way that, if you're familiar with these methods, but just at a high level, these are the methods that adjust the loss function in order to learn with noisy labels. But these ones that perform the best are the ones that actually they modify the training data. And so this is a very clear indication that there is something to this data-centric AI. From an actual benchmarking perspective, you can show that data-centric AI methods tend to outperform. And for folks in here who are interested in data-centric AI, this is a motivating result that you can check into and see, hey, there's something behind this data-centric AI besides the hype. So I'm short on time, so I'll just show two more things. You can check out some of the use cases for AI for data correction in this blog post, and see how does Google use Cleanlab, how does we use it at Facebook for various things, for cheating detection at MIT and Harvard, and you can look into that. We also use it at Andrew Ng's Data-Centric AI competition, where you could show, that you can find, really clear errors in that competition. And there's a bunch of other use cases, but in general, check out the open source. These algorithms are all freely available. While I was doing my PhD at MIT, I just put everything online and shared it so that I could get feedback. The real reason, if folks are interested, for why we open source this was because people had trouble believing that you could actually just find errors in any data set. And so we open sourced it, which sort of addressed those questions. So the sort of final two things is, one, this is a general framework that you can use if you want to find errors in your own data set using the open source. So it's just one import. You import Cleanlab and then one line of code. So in one line of code, you can find errors yourself. It's just the clean learning module. You pass in whatever classifier you like, and then call .find label issues with whatever your data is. It can be a data frame, and just like a list of labels. And then the final last thing I wanted to show was just very briefly Cleanlab Studio. And the idea behind Studio was, can we make AI for data correction accessible to everyone, right? So if you build something, you say, hey, this is practical. Like, let's actually have a tool where with no code, entirely automatically, you can drop a data set and you can find all the errors and correct them, in an actual SaaS automated way. And so that's what we built at Cleanlab. And this is intended to be a techniques and academic talk, so I won't go into it in detail. I'll just show you. So here's Cleanlab Studio. This is a real world data set, Amazon. This is saying one of the best magazines. It's so fun to come to this delivery. And, this is something that we looked at in advance. So we checked. We don't use this column in Cleanlab Studio, but we checked that we know this is a label error. And you can see that the given label is 1. And then all of these things are computed automatically for you. So you get like a ranking over every example, whether it's true or whether it's an error or not. And then we give the corrected label for you. And so this is we just dropped this data set and it's done for you. Yeah, that's all I've got. If you want to contact me, you can do so here. And the neat thing is it works with any data framework. So whatever your data set is. So yeah, here's the main contributions and how to contact me at the bottom.